This is the second half of our review, and in this question we are finding the orders of elements, of groups. So we have D4, U21, excuse me, that's not 27 here, U21 and Z10. So in D4 we know the orders of elements, but of course you have to know what the order of an element is. It's the least, excuse me, the least integer, such that when you raise that element to that integral power, you get the identity. So in D4, we know that the order of R is the same as the order of R cubed is equal to 4. Because if you generate the little subset, you'll get R squared, R cubed, and the identity. Whereas the order of R squared is 2, and so is the order of H, the order of HR, HR squared, and HR cubed. They all have order 2 because when you square them, you get the identity. So this is a very familiar group. Notice that we have elements of order 2, and we have elements of order 4, and the order of D4. Now, when we say the order of a group, we mean something different. Same notation, but we mean the order of D4 is the number of elements in the group. So the order of D4 is 8. Notice that the order of the elements, 2 and 4, both are divisors of 8. Now in U21, I'm going to need a lot more room than I put here. And notice I changed these groups a little bit too. We're looking at Z15, not Z10. But just go along with what I wrote below. Okay, U21. Let's see, U21 has 12 elements in it. So the order of the group itself is 12. And now we're going to look for the orders of its elements. Now I'm not going to do all of them here, but let's kind of ignore Z15 for now, and I'll write that over again later, and we'll do it. I obviously didn't leave myself enough room for this U21. Now it's kind of, oh boy, hang on. Okay, so I moved the slide and wrote down U21 where we'd have more space to work. And notice over at the side, I just jotted down multiples of 21. Because when we do arithmetic in U21, we're always multiplying and throwing out multiples of 21 so that we get the remainder upon division by 21. So let's find the subgroup generated, the subset generated by 5. Okay, so we have to do this in order to know the order of 5. So we put in 5. 5 times 5 is 25. And I throw out 21, subtracting 21, so I have 4, remainder of 4. And now notice when I get 5 cubed, I don't go 5 times 5 times 5. I go 5 times 5 squared, 5 times 4. So 5 times 4 is 20, and that's 20 mod 21. Now 5 times 20, keeping to multiplying by 5, but doing it mod 21. So 5 times 20 is 100, and I go down here and I see, oh, okay, so 84. So subtract 84 from 100, and I have 16 mod 21. Now multiplying 16 by 5, I have 80, and subtracting 63, I'll get 17. Multiplying 17 times 5, I get 85, and 85 is congruent to 1. So there's my identity, and that is the cyclic subset generated by 5. Notice it has 6 elements in it, so we say that the order of 5 is 6. Remember, the order of the group itself, the order of U21 is 12. So we keep that in mind, and we find that the order of one of its elements is 6, a divisor of 12. Let's find the order of another one. Let's take 20. We have to generate the cyclic subset generated by 20. So I put 20 in first. 20 times 20 is 400. So let's see, I could divide 400 by 21 and get a remainder, but I'll just subtract 252. That was the last power I had, and I would have 148 as a remainder. And then, 147, to subtract out 147 more, and I have 1. So you just subtract out multiples of 21, because you're doing your arithmetic mod 21, until you have a remainder, something less than 21. And here we see it's the identity. So the order of 20 in U21 is 2. Notice 2 is a divisor of the order of the group. Let's find the order of 4. So I need the cyclic subset generated by 4. Put 4 in. 4 times 4 is 16, which is 16 mod 21. 16 times 4 is 64. And if I take out 63, I get the identity. So we see that the order of 4 in U21 is 3. Another divisor, in fact, of the order of the group 12. And if you do all of these, you will find out that the order of the elements in U21, the order of the elements are either 1, 2, 3, 4, 6, or 12. You won't necessarily get elements of all of those orders. I don't think I found one of order 4. I did several of these, but the order of these little cyclic subsets, the elements themselves generate little subsets, and the order of them is always a divisor of the order of the group. That's an important theorem that we're going to prove in our next handout that you have, handout 3. And these little subsets that we're generating, the first thing that we're going to consider in handout 3 is that these little subsets, these little cyclic subsets, are in fact groups all on their own. So they're going to be called subgroups instead of subsets. Look at the yellow numbers up here that I put near the elements of U21. That's what I came out with as the order of those elements. Now I just was doing quick arithmetic on the side, so if you guys find that one of those is incorrect, don't spend too much time looking at it, because I could have made an arithmetic mistake, but that's what I came up with, and I know for sure that the order of the elements will always be a divisor of the order of the group. So if you come up with 5, for example, you know you made a mistake, because it's not a divisor of 12, which is the order of U21. Now for our Z groups, we know that the operation is addition mod 15. These are nice little abelian groups. The order of Z15 is 15, and the operation again is multiplication mod 15. Now another thing that we have learned is that if the element is relatively prime to 15, that if we keep multiplying it to itself, we'll eventually get to the identity. So let's just see that in one example. Let's take, 2 is relatively prime to 15, so let's just generate the powers of 2, and you'll see what happens. So we have 2, and then 2 times 2 is 4, 2 times 4 is 8. 2 times 8 is 16, which is 1. 2 times, oh goodness. You guys, I don't have time to do this over because I just misstated. It's addition mod 15. 2 plus 2 is 4, plus 2 is 6, plus 2 is 8, plus 2 is 10, plus 2 is 12, plus 2 is 14, plus 2 is 16, which is 1, plus 2 is 3, plus 2 is 5, plus 2, 7, and then we get 9, 11, 13, and plus 2 is 15, which is 0. So you see that addition mod 15, 2 generates the entire group. And you will see that this is true of any of the numbers that are relatively prime to 15. So in fact, we could say Z15 is equal to the cyclic subset generated by 2, same the one generated by 4, 7, 8, 11, 13, and 14. I guess you can't see that. Okay, so those are all the numbers relatively prime to 15, and they generate the whole group. Let's try another one. Let's take 3. 3 is not relatively prime to 15, and it won't generate the entire group. So let's see what we get. Starting with 3, 3 plus 3, add 3 more, add 3 more, add 3 more, we get to 0. So we see that the order of 3 is equal to 5, a divisor of 15. The order of all these elements up here were 15. Let's see, let's try another one. How about let's do 6. The cyclic subset generated by 6. Starting with 6, 6 plus 6 is 12, plus 6 is 18, which is 3, and 3 plus 6 is 9, and 6 plus 9, we get to 0. So we see that the elements 3 and 6 generated the same subset or subgroup. And so we would say that the order of 6 is also equal to 5. Let's do one more. Let's go back up here. Let's do the cyclic subset generated by 5. Starting with 5 and remembering to add, 5 plus 5 is 10, plus 5 is 0. So the cyclic subset generated by 5 has 3 elements in it, telling us then that the order of 5 is equal to 3, another divisor of the order of the group, which is 15. Now, the last example in this problem was Z7. Z7, the order of Z7 is 7. It has 7 elements in it. And it's prime. 7 is prime. So none of these numbers in here are they're all relatively prime to 7. So in this case, every element will generate the whole thing. And so we could say that Z7 is generated by all of its non-identity elements. 1 is generated by 2, is generated by 3, and so on. It's generated by 6. And if you try, you'll see you get the whole thing. The order of Z7 is 7, and notice 7 has no divisors. So it's not surprising, after what we've observed in the previous examples, that all of the non-identity elements will generate the whole group. This was the set or the group of linear functions from R to R with a non-zero coefficient of x. Classify all elements of order 2. We did this in class. The main thing is when you write something like this, f squared equals the identity, we'll call it little I, we don't mean f times f, do we? Because the operation in this group is function composition. So what this means when we say a function has order 2, we mean that f circle f of x is the identity function. And the identity function, well, you could go ahead and say I of x, but what was that? I of x gives you x. The identity function is just y equals x, or f of x equals x. So we want to solve f of x equals x. What functions will satisfy this? Well, in general, let's just let f of x be equal to ax plus b, where we know a is not 0, and let's just see what this gives us. F of x then is equal to, well, it's equal to f of a, this implies that f of ax plus b is equal to x, which implies that a times ax plus b is equal to x. Simplifying this, we get a squared x plus, and then we have ab plus b. So let's factor out the b and say b times a plus 1 is equal to x. Okay, so we want to classify these functions. In other words, what would be true about the coefficient of x, a, and b, in order to have this equation b hold? Well, it would mean that a squared was 1. This is 1x plus 0. So a squared would be equal to 1. And b times a plus 1 would have to be 0. Well, this means a is equal to plus or minus 1, and b equals 0, or a equals minus 1. All right, so if a is minus 1, this part is taken care of. So one function, one way to do it is just to make a equals minus 1, and b could be anything. So this gives us all the functions of the type f of x equals minus x plus b. All of those functions, minus x plus 3, minus x plus 4, those all will be of order 2. Now, if a is not minus 1, if a is equal to 1, then b has to be 0. So this gives us the function y equals x, the little iota of x. This is the identity function, I of x equals x. And we know that the identity, always when you square it, you get the identity. But the other ones are these functions here. And I suggest that you take, like, let f of x be minus x plus 4 and compose it with itself and see that you do get x. In other words, f of x is equal to little iota. The second part asks us to find an element of infinite order, one that no matter how many times you compose the function with itself, you will never get back to the identity function. Well, let's just try one here. How about, this pen isn't working. Okay, how about, let's say g of x equals x plus 1. Then let's see, g of x will be, well, the rule for g just says add 1. So it's going to be x plus 2. And if you want to write g cubed, you can. It means, though, g of x is going to be x plus 3. And so you see this just goes on forever, and you will never get back to the identity. So g of x equals x plus 1 is an element of infinite order in the group of linear functions with non-zero coefficients on x. Okay, here we have a matrix in the general linear group of 2 by 2 matrices, but the entries in these matrices come from Z5. So that means all of the calculations we do are in Z5. And it says find A inverse. So by the way, this group here is a finite non-abelian group of matrices. All of our other groups of matrices we've looked at have been infinite. But if we only let the entries come from a set containing 5 elements, we know that there won't be an infinite number of matrices. All right, so, well, we know that A inverse will be equal to 1 over the determinant of A times the matrix, switching on the main diagonal, changing the sign along the other diagonal, this. But the additive, we don't read minus 2. It's not negative. It's the additive inverse of 2 and the additive inverse of 3 and the multiplicative inverse of the determinant of A. That's what we're doing. It's the same in the real numbers, except we tend to think of negative 2. But what is it? It's the additive inverse of 2. So let's calculate the determinant of A. The determinant of A is 3 minus 3 times 2 is 6, which is 1. So it's 2. And so we want 2 inverse. And the inverse of 2 is 3, because 3 times 2 is 6, which is congruent to 1 mod 5. So this is equal to 3 times the matrix, 3. The additive inverse of 2 is 3. The additive inverse of 3 is 2, and 1. Multiplying that, we have 3 times 3 is 9, which is 4. 3 times 3 is 9, or 4. 3 times 2 is 6, which is 1, and 3 times 1 is 3. Now you can check this. Take the matrix 1, 3, 2, 3 here, and multiply it to 4, 4, 1, 3, and see that you do get the identity, and you will. You get 1, 0, 0, 1. But do it. Get the practice in working with modular arithmetic, both in multiplication and addition. Prove that in a group, the inverse of AB is B inverse A inverse. This is a very simple proof because you look at this and you say, well, what is this thing? It is the inverse of AB. It is the element that when you multiply it to AB, you get the identity. So let's take B inverse A inverse and multiply it to AB. And you see that we have the associative property. So that's the same thing as B inverse A, B, by the associative property. This is the identity. And B inverse B is the identity. You get the identity. And try it on the other side. AB times B inverse A inverse. And you'll also get the identity. So you can say, therefore, B inverse A inverse is AB inverse, because AB inverse is unique. So this last equality is by the uniqueness of inverses. And by the way, you should be able to prove that inverses are unique. That's in the handout. We proved it in class. Now, under what conditions could we say that AB inverse is equal to A inverse B inverse? Well, we know we always do that in the real numbers, don't we? But that's because it's an abelian group. So we know that AB inverse, we just proved that it's B inverse A inverse. And when can we change it around? Well, when the operation is commutative, or when the group is abelian. The group is abelian, or you could say the operation is commutative. Well, let's prove that a group is abelian if and only if this holds. We've already done half of this. Suppose it's an if and only if, so we have to suppose G is abelian, and then prove that this is true. Well, we just proved that AB inverse, this you can use now, is B inverse A inverse. That's by what we just proved the problem before. And if G is abelian, that's A inverse B inverse. So we're done. Now suppose that AB inverse is A inverse B inverse, and we want to prove that the group is abelian, the operation is commutative. Well, this implies, by what we just proved, that B inverse A inverse is equal to A inverse B inverse, because we know in any group the inverse of AB can be written B inverse A inverse. And now what we can do is, let's multiply on both sides by, well, I'm going to multiply on the right by BA, and over here by BA. Notice I do not multiply on the left on one side and on the right on the other, because we don't know that G is abelian. So I have to make sure to multiply on the right. And so I have here B inverse A inverse BA is equal to, and notice the B's cancel, the A's cancel, so I get the identity. Now I'm going to multiply on the left by, well, I'm going to multiply by AB on the left. And what I get is, well, now these cancel, B inverse, A inverse. I get BA is equal to AB, G, therefore G is abelian. This problem is actually pretty easy, because I gave you the hint that make a table. You've only got 3 elements. So let's let G contain, we know it has an identity, and 2 other elements. It's a group, so it has an identity. And now let's just see how we could fill out a chart. If we have E, A, B, it's some operation, E, A, B. Well, the identity will just give us that row back again, and the first column back again. And now we have to decide how can we fill it in. All right, well, let's just look at this middle entry here. What could we put in there? We could put, well, we've already got A, so we could put E or B. Now consider that. If I put E here, then I would have to put B here. B cannot go in that column because it's already there. So I have to put B here. Now, once you've made that choice for B, everything else is determined. A, B, E. A, B, E, and you have to put A here. The only thing you had to reason out was, is there one thing I need to put there? Yes, if you tried putting E here, you would have had to put B. And you know, in a table for a group, in each row and in each column, you have every element of the group appearing once. So there is only one way to fill out the table, and therefore there is simply only one group, essentially, of order 3. Might have different names, different operation, but the group table would always look the same. And here are, I believe, all the groups that we have looked at. We have finite groups and infinite groups. We have abelian and non-abelian. And you should be able to operate in each and every one of these groups, knowing what the operation is and what the elements of the group are. So the simplest groups we looked at were the ones that we had looked at for years in school, and it's just the infinite groups of integers, rationals, and reals, and then the 2 by 2 matrices. Under addition, and that of course was abelian, but the 2 by 2 matrices under multiplication, the general linear group of matrices with non-zero determinants, that's an infinite group, but it's not abelian. So study this, and this is the last slide, so I hope you guys all study really hard.